Okay, good day everyone. I'm Engineer Denver Magtibay, Sir Poggy, and our topic for today is all about electronic instrumentation. Okay, before we start our topic, let us have first the verse from 2 Corinthians 12 to 9. He said to me, "My grace is sufficient for you, for my power is made perfect in weakness. Therefore, I will boast all the more gladly about my weaknesses, so that Christ's power may rest on me." So, that is our Bible verse for this subject. So, we are weak, but God is strong. We are foolish, but God is wise. We are limited in our own ways, but God is limitless. So let us leave everything to God. Let us do our best every time and let God do the rest. Okay, so let's start. So our topic is all about instrumentation. And what is instrumentation? So instrumentation is a collective term for measuring instruments used for indicating, measuring, controlling, and recording physical quantities. So it's also defined as development and use of precise measuring equipment. So this refers to instruments ranging from basic test instruments to complex scientific instruments. So we're about to tackle those instruments here. Let's proceed. So here we have instruments. So what is instrument? Devices that can give quantitative description on a given parameters. They provide visual indication of the quantity being measured. The instrument sometimes furnishes a permanent record. So the basic functions of the instruments are as follows: indicating, recording, controlling for industrial situations, and monitoring remote signals. So these are the electrical units that we will encounter as we go along. So as with any quantitative science, a system of units is required before one can make a quantitative evaluation of parameters measured. So these are the SI units. You can see the SI units for length is meter, for mass is kilogram, and we have seconds for time, candela for luminous intensity, Kelvin for temperature, and ampere for electric current. So in instrumentation, we have several standards that we need to follow. So these are called measurement standards. So instrument or device having a recognized permanent value that is used as a reference or criterion. And one of those standards that we have is what we call the international standards. So what do we have in this international standard? So defined by international agreement and standards maintained at the International Bureau of Weight and Measure in Paris. So take note of that. Okay, next we have our primary standards. So it's maintained at national standards laboratories in different countries. And National Bureau of Standards in Washington is responsible in maintaining the primary standards. Then we have our secondary standards, basic reference standards used by measurements and calibration laboratories. And then last, we have our working standards. It's the principal tools of measurement conforms to the expected value, and it is used to check and calibrate the instruments used in laboratory or to make comparison measurements in industrial applications. Okay, so working standards, this is the standard that we are using when we are in our laboratories working for experiment or in industrial application. We are following certain standards. We call that the working standards. Okay, so next we have our errors in measurement. So what is an error? It is the degree to which measurement conforms to the expected value. So it can be expressed as absolute, or it can be percent of error. So what is an absolute error? Well, absolute error is defined as the difference between the expected value of the variable and the measured value of the variable. So expected value are also called, can also be called the true value. Okay. Yeah. And then, so the formula for our error is expected value minus the measured value. And to get the formula for our percent error, it's just the absolute error times 100 all over the expected value. Okay. Next we have accuracy. What is accuracy? It is the degree of exactness of a measurement when compared to the expected or the most probable value of the variable being measured. So the formula of accuracy is just 100% minus the percent error. Next, if we have accuracy, we also have our precision. So precision is the indication of the closeness with which a repeated set of measurements of the same variable agrees with the average of the set of measurement. Okay, so when we say precision, it's the closeness of the values when we repeat the measurements. So if we compare the precision and accuracy here, the first figure, we can say that this is precise because the values are close to each other, but it is not accurate because the values are very far from our target, or we call this the expected value or the true value. Okay, and the next figure, the values are close to the true value, but they are not precise because they are not close to each other. So we can say that the second figure is accurate but not precise. The third figure is both not precise and not accurate. As we can see, the values are far from each other, and also the values are far from the true value. And lastly, we can have a measurement which is both precise and accurate. As we can see, the values are close to the expected value, and at the same time they are close to each other. Next, we have the types of errors, different types of errors that we have in instrumentations and measurements. The first type is called the gross error. So what do we have in this gross error is that they are errors which are generally the fault of the person. So take note, the fault of the person using the instruments, and are due to such things as incorrect reading of instruments, incorrect reading of experimental data, or incorrect use of instrument. In short, gross error is the error of the person due to lack of knowledge on how to properly use the instrument. Okay, so let's proceed. Next, we have systematic error. When we say systematic error, so we have errors due to problems with instruments, environmental effects, or observational errors. So we have different kinds of systematic errors here. The first type is the instrument error. Okay, so what do we have in this instrument error? Is due to friction, in the bearings of the meter movement, incorrect spring tension, improper calibration, or faulty instruments. In short, instrument errors is due to the instrument itself. Maybe the instrument is already old, or it's used for a long time and it becomes faulty. And then we have the next type of errors, what we call the environmental errors. Subjecting instruments to harsh environments such as high temperature, pressure, and humidity may have detrimental effects, causing error. This type of error is more on the outside factors, particularly the environments. Okay? And then the third kind of systematic error is what we call the observational errors. And those errors introduced by the observer on how the observer looked on the instrument. So the most common observational errors are called the parallax errors. So introduced in reading a meter scale and the error of estimation when obtaining a reading from a meter scale. So most especially when we are about to take a reading from an analog meter, wherein we estimate, or depends upon the angle on which we look, we will have different kinds of errors, and we call those errors the parallax errors. Then we have the random errors, accumulation of a large number of small effects, maybe of real concern only in measurements requiring a high degree of accuracy. Okay, so those are the kinds of errors that we have. So to wrap it up, we have the gross error due to the person, systematic errors, different types. We have instrument errors, environmental errors, and observational errors. And then we have random errors. Okay, so next we have meter movements. So the basic meter movements in analog type meters, they use direct current measurements and can be traced to Hans Orsted's discovery of relation between current and magnetism. So let's proceed. First type of movement is called the Arsonval movement. So we have the Arsonval movement, or the permanent magnet moving coil meter movement, or the PMMC meter movement. Okay, so it's another term for the Arsonval. So it uses a torque band suspension system which provides a more sensitive meter movement. And take note, these are the parts of the Arsonval meter: moving coil, a spring, and a permanent magnet. So take note, you see permanent magnet, moving coil, and spring, automatically it will be the Arsonval meter, or the PMMC. Then DC use, but can also be used in alternating current application only if, so take note, only if it has rectifiers. So it can be used in direct current, but can also be used in AC. Take note, only if it has rectifiers. Okay. So most widely used meter movement for measuring direct current or voltage and resistance. So take note, it is specially used, it is mostly used for DC. And errors in PMMC are due to, so we have spring aging and magnet aging, and of course temperature. So those are the types of cause of errors in PMMC. Okay, let's proceed to the next. Okay, the types of torque in the Arsonval meters. We have three types of torques. First is we have deflecting torque. So deflecting torque, or we call this the moving torque. This is required to move the pointer from its 0 position. So take note, from its 0 position. Then we have the controlling torque. It's produced by spring action and opposes. So that's the key word that we have. It opposes the deflection torque, so as the pointer can come to rest at the point where these two torques are equal. And the last, we have the damping torque. This torque ensures the pointer comes to an equilibrium position at rest in the scale without oscillating to give accurate reading. So take note, for damping torque, it is on the equilibrium position. It is on the time that we are about to read the measurement of the meter. The next type of meter movement is called the electrodynamometer meter movement, or meter. So it consists of a moving coil. So take note the parts of this meter. Moving coil called armature that is free to move within a magnetic field set of two stationary field coils. So take note, where's that stationary field coils? This is the stationary field coils that we're talking about. And then we have the moving coil. The moving coil is right here. It's a moving coil. And it can measure direct current and alternating current. So some applications include standards meter transfer instrument, and the most famous application of electrodynamometer is for watt meter. So tatandaan natin yan. Okay? And of course, frequency meter. Next is what we call the iron vane movements. So it consists of fixed coil of many turns and iron vanes placed inside the fixed coil. So that is our keyword, iron vanes. So the name itself, iron vane movement. So it is responsive to direct current. Take note, it is for direct current, DC. Has a square law response, but the fixed coil can be designed to provide a relatively linear response. So the soft iron vanes are fastened to the shaft that drives the pointer and are free to move within the magnetic setup by the inclined coil. So its application is for indicator applications, such as in automobiles. Take note of that. Next, then we have the electrostatic meter movement. So an indicating mechanism resembling variable capacitor. That's the keyword, variable capacitor. Okay, yes sir. And the only mechanism used for electrical indications that measures voltage directly rather than by the effect of current. So take note, it is directly measuring voltage rather than current. So some applications include measurement of high voltage when very little current can be supplied by the circuit being used. And of course, it is used for alternating current and direct current. Next, we have the thermocouple meter. So instrument that causes heater element usually consists of thermocouple and the Arsonval meter movement. So it is a combination of thermocouple and the Arsonval meter movement used for AC and of course DC. So its most notable function is to measure very high frequency, so very high frequency AC, and accurate above 50 megahertz. So senses the temperature of the heater wire, which is a function of the current and the voltage being measured. So thermocouple and the heater must be thermally coupled but electrically isolated, and it can also be used to measure AC and DC.